Assalamu alaikum. Hello, everyone. We continue the topic of basic classification methods. So for the first few cells, I have already explained them in a different set of slides. I just want to mention a few things before we start from where we left off last time, okay? So first of all, for the classification problem, there are three major types for classification problems. There is what we call one-class classification problem, binary class classification problem, and multi-class classification problem. The last two are the popular ones. In a binary classification problem, there are two classes. In multi-class classification problem, there are more than two classes. There's also what we call one-class classification problem. The aim here actually is to capture the characteristics of the training samples. So in the operation phase, we will be able to distinguish between them and any potential outliers, okay? So for binary classification problems, the class label can take like any of these choices. The class labels could be yes and no, true, false, positive and negative, 1 and 0, -1 and 1, and also 1 and 2. So here 2 is for identification. So there's no order here. Okay, you can give any two numbers. Okay, so they meant to be for identification. So the type is nominal here. Same here for like if we have more than two classes, then we can give them integer numbers 1, 2, 3, 4. And as I said, this is not meant to introduce an order. This is just for identification. Okay, so there is no order here. They are just this is of type nominal. The numbers here are just for identification. We also can give A, B, C, okay, to identify different classes. So this example, we will come to this later on. I don't need to go through this example for now because we're not actually doing anything here. We're just loading the data. We're going to come and defining the different attributes. We're going to come to that later on. So in my previous video, I explained decision tree at very high level, okay, as a classification method. And here, I have already explained this, but I just want to mention something here. As I said, the goal, like when we are learning, okay, when we are training a decision tree is actually to, at every node, is to actually choose which feature to choose and what condition to build such that the uncertainty is minimized, okay? And in order to do that, there are different algorithms, okay, or approaches to use. One well-known approach is what we call iterative dichotomizer tree, ID3 approach, okay, which relies on entropy and information gain in order to define the uncertainty, measure the uncertainty and make a decision at any node what feature to choose and which condition to build. And we're going to come to the details later on, okay? So we're going to actually spend some time actually explaining uncertainty in more details and how to quantify it using entropy, and then how we use all of these in order to build decision trees, okay? I just want to mention here, like ID3 is not the only approach. There are some other mechanisms and approaches, but in this course, we will focus on this approach, which actually breaks or because dichotomization is like breaking or dividing. So breaking and dividing the data into subsets based on based on the value of the entropy and the information gain, we decide which feature to use to break the data at any given node. Okay, let me go back. Here we're gonna spend some time understanding uncertainty first, and then how we quantify it using entropy, and then we go back to how to build decision trees using this approach, ID3 approach. Okay, so let's start with this example here. So here we have 12 books. Everyone has a red color. Okay, so here there is no uncertainty because simply if I randomly select one book, I'm sure that the color will be red. So there is no uncertainty here. Okay, so now if I introduce, if I change the last two books, okay, to with blue box, now there is some uncertainty here, okay, because actually if I randomly select a book, okay, there is like probability 0.8 that book is red, and with probability 0.2 the book will have a blue color, okay. So there's some uncertainty here, okay. Now as I introduce more blue box here, okay, now the uncertainty will be at its like it will be the highest when they are equally probable. Okay, these are two classes. Now they are equally probable because there are five books, okay, five red books and five blue books. So the uncertainty here is very high, because if I randomly select a book, it will be with equal probability of it will have equal probability of being red and or blue. Okay, the probability is 0.5 here for the red category or class, and 0.5 for the blue class. So the uncertainty here is very high. So we need like a metric that goes to zero, that has a value of zero when there is no uncertainty, when we are sure or certain about the decision. It goes to zero, and it goes to its highest value, okay, when the uncertainty is so high, okay. And that metric actually is the metric we're using here is the entropy, and we're gonna come to what entropy is, but let me just uh, finish this video first. So this is like, here we assume two classes, okay. Now if we have more than two classes, for example here we have five classes, there are five choices for the color, and every two books are of one of these colors. The first two books are red, the second two books, the second, like the third and fourth books are of they have a gray color, and so on. So here all of these classes or choices are equally probable. Here the uncertainty is very high, it's actually the highest here, okay. Now let's come to how we quantify the uncertainty. As I said, we use the entropy, okay. So the goal here, actually, this is how we compute the entropy. It's minus negative of this summation, sum from I equal 1 to k p of I log 2 p of I, where p of I is the probability of class I. And here there are, like we sum from I equal 1 to k is the number of classes or choices. For example, for this example here, we have two choices, red and blue. So then k will be equal to 2, okay? And we use log 2 here. I'm going to come to explain that later on. So why we use log 2, and also we're going to explain the unit of entropy, which is called bits, and we're going to come to explain that later on. But now let's just spend some time understanding this formula and how we use it to quantify the uncertainty. The first thing I would like to mention here, entropy is a positive entity. So because here we compute log 2 of the probability, and the probability will always be less than or equal to 1. So this term will always be negative, and we have negative sign here. So the entropy will always be greater than or equal to 0. Okay. And since it quantifies the uncertainty, then we want it to go to 0 when there is no uncertainty. For this example here, there is no uncertainty, then we want the value of this to be 0. And here, the highest uncertainty, we have it here when they are equally probable. So we want this to reach its maximum for this example, okay? So let's see if that's the case. Okay, let's examine this formula here. And I created this example here in order to explain that formula, okay? So let's look at this example here where we have two classes, okay? We have red and blue colors. So we have two classes. So then if we want to compute the entropy of the color, so our random variable here, or our attribute is the color. The color can take red and blue values, okay? One of these two. So there are two choices. So then if I want to compute the entropy of color, it would be a minus of this summation, right? Probability of red times log 2 probability of red plus probability of blue times log 2 probability of blue. And we know, like, the probability of red plus blue should sum to 1, right? Because the book is either red or blue. Then if we define probability of blue to be equal to P, then probability of red will be equal to 1 minus P. Then this formula can reduce to this one. 1 minus P times log2 1 minus B plus B times log2 of P. Now let's examine this at three choices for P. Remember, P is the probability of blue. Okay, we will examine it at P equal to 0, P equal to 1, the two extreme points, and the one in the middle. Okay, so when P equal to 0, this means this actually reduces to this case. Okay, all of the books are red, so there is no uncertainty here. So when P equal to 0, then we need this to be 0, right? Let's look at the value of this. The entropy of the color is equal to 1 minus P is equal to 1 because B is equal to 0. 1 times log2 1 plus 0 times log2 of 0. So log2 of 1 is equal to 0. This term is equal to 0. Here, log2 of 0 is undefined. Okay, but here, so if you run this using a Python code, you will run into an error. Okay, but actually, here we take it equal to 0. 0 times undefined, we just set it to 0. Okay, so this is equal to 0. And that makes sense, right? When there is no uncertainty, then the entropy should be equal to 0. And this is what we got. Okay, that's for the first point. Let's take the other extreme. When P is equal to 1, when all of the books are blue. Okay, so then it's the same case, right? There's no uncertainty here because, yeah, there's no uncertainty because if I randomly pick a book, it will have a blue color. Okay, so let's examine this formula under that choice of P. So when P is equal to 1, 1 minus P is equal to 0, 0 times log2 of 0 plus 1 times log2 of 1, and log2 of 1, as I said, is 0, then this is equal to 0. So in these two extreme points, the probability will be equal to 0. So the entropy will be equal to 0. So there will be no uncertainty, and that makes sense, right? So I mean, now the entropy goes to 0 when there is no uncertainty. Now let's look at the case when P is equal to half. Now the uncertainty is very high. Okay, here, if I randomly pick a book with probability 0.5, it will be red, and with probability 0.5, it will be blue. So the uncertainty is so high. Let's see what the value of entropy here. So entropy of the color will be equal to half log2 of half plus half log2 of half, okay? And log2 of half is equal to minus 1, right? So then this will be, okay, so there is, I need to fix this here. Okay, this is equal to 1. Okay, so because this will be actually half, minus half minus half, okay, that is minus 1 times the negative sign outside, that will be equal to 1. Okay, so when they are equally probable, the entropy is equal to 1, and that's the highest if I have two classes. Okay, this is the highest value of the entropy if we have two classes. In fact, we can plot it here, and in fact, it's plot, yeah, here we have the figure. It goes this way. So it reaches the highest when P is equal to 0.5. So it will be exactly at 1. Okay. And here we are plotting, we're starting from 0.1 to 0.9, because if we pass 0 and 1, we will run into an error. Okay. But that's how the entropy of P versus B would look like. Okay. Now, now we have been looking at the entropy of the color. So we are looking at the entropy of this attribute. Now we're gonna move to what we call the conditional entropy. Okay, the entropy on one attribute given the value of another attribute. If I have more than one attribute, now if I know attribute B, will that tell me something about attribute A? So entropy actually can capture even non-linear dependencies. Okay, if there is any non-linear relationship between B and A, so then if knowing B tells you something about A, then the conditional entropy of A given B should be lower than the entropy of A. And we're going to come to those details. Let me just be very brief for now, but these details will come later on. So let me look at the conditional entropy, okay? So the conditional entropy of A given B is of this form, okay? So maybe before I explain this form here, let me look at the example, okay? Here, this example here, and then we're gonna come to the form. The form will become more clear after we look at the example, okay? So here we assume we have two attributes. We have the color as well as the subject. Okay, so here, now let's look at the color first. Here we have how many? Okay, we have 5 red books and 5 blue books. So the uncertainty is so high and the entropy is equal to 1. Okay, and we did calculate that. Okay, now we are looking at color isolated from any other attributes. Okay, now this is the color when we have 5 classes. Okay, so the probability of each one is 0.2. So we will have 0.2, log 2, 0.2, and we have 5 of them. Okay, we can just do 5 times that. Okay, times the negative sign outside, then the entropy of color will be equal to 2.32. So if I have more than 2 classes, the entropy can go higher than 1. And in fact, for 5 classes equally probable, this is the highest you can get. Okay. I mean, and for 5 classes in general, this is the highest. The highest you get when they are equally probable. This is the scenario where they are equally probable. Okay. Now let's look at this here. So here we have another attribute, call it subject. Now, if you look at this figure here, okay. So if I look at the color isolated from any other attribute from the subject, then the uncertainty is so high. Okay, here the uncertainty is so high and the entropy value will be equal to 2.32. Okay, but if I actually look at the uncertainty on the color given I know the subject, or the entropy of the color given the subject, actually you can see if I know the subject, I will know the color, because all math books are red, all physics books are gray, and so on. So if I know the subject, I will know the color. There's no uncertainty on the color. The uncertainty went all the way to 0. So when I look at the color, okay, isolated from the subject, the entropy is 2.32. Now, and the uncertainty is at its highest level. Now, if I know the subject, then there is no uncertainty and the entropy will go to 0. Okay, let me show you. Yeah, let me run the video and then we explain it further. Okay, as you can see here, so these are like the different splits, because yeah. So this is the entropy of the color given the subject is equal to math. So in fact, how do we compute the conditional entropy? Here, the conditional entropy of the color given the subject is equal to the probability that the subject is math times the conditional entropy of color given subject is equal to math, plus the probability of the subject being physics times the conditional entropy of the color given that the subject is physics, plus the probability of the subject being chemistry times the entropy of the color given the subject is equal to chemistry, and so on. So we sum all of these. So this is the formula we have here. Now this example made it clear. This is the probability of the jet choice or class for attribute B, the other attribute. Okay, so this is the probability of the jet class for attribute B times the conditional entropy of A given B is equal to Bj. Okay, that choice. Okay, so hopefully this example explain it like this formula. And in fact, this is also another way to write it. Okay, it's the probability of the jet choice times entropy of Aj, and entropy of Aj is entropy of A given B is equal to the Bj, the jet choice or class for B, attribute B. Okay, so that's it. Now, if we look at this here in this example, okay, probability of math is equal to 0.2, okay, times what? Times the conditional entropy of color given the subject equal to math. So the conditional entropy of the color given the subject is equal, math is equal to 0. There is no uncertainty here. And you can actually compute it, right? It's just this, right? So it's in fact there are if you want to compute it for like entropy of color given the subject is equal to matte, then you look at the different like what are the probabilities. So in fact all of them are zeros except the probability of red, which is equal to 1. So then you will get 0. Okay, and visually just looking from here, you don't even need to do any computation. So like there is no uncertainty, so the entropy will be equal to 0. So that's why we have 0.2 times 0 plus 0.2, okay, the probability of the subject being physics times the entropy of the color given subject equal to physics, that's equal to 0. So then the answer is, why I'm not writing that? Okay, that's equal to 0. Okay. Okay, so then the entropy, the conditional entropy of color given subject is equal to 0. So then actually this tells me everything about the color. Okay, the dependency is so high here. And we're going to come to more details later on. And in fact, even how to compute this conditional entropy exactly, we're going to have examples coming later on. So we will do all of that. Okay, it's coming, inshallah. Now I just want to explain something. When I talked about the unit of entropy is called bits, this is actually coming from the information theory. The entropy is actually can be seen as the lower bound on the average code length when you are designing a communication system, when you are considering transmitting samples from one transmitter to a receiver, then you need to design your code. Okay, so I will explain it at very high level. The students who will actually later on choose the measure of communication and signal processing, they will get to know this in more details. I will be very brief here just to explain where the unit bit is coming from. Okay, so simply when we have a communication system, we have a transmitter and a receiver, then our goal is to transmit is to convey messages between the transmitter and the receiver, but we need to send the minimum number of bits because sending more bits will require consuming more resources, power and bandwidth, and these are limited resources. So we don't want to send so many bits. So we try to minimize the number of bits. Then the entropy can actually give you a theoretic lower bound in the average code length you can send for different samples. For example, here we assume a transmitter that can send one of these 4 samples, A, B, C, and D. Okay. Now, if they are equally probable, you compute the entropy for that. You find you want to send an average 2 bits. Okay, that's the minimum you can send because they are equally probable. Okay, so you need to send 2 bits. So you will use 00 for, and I should have added that here. You will use, okay, very quickly, sorry. So you will use something like this. A will be 00, B will be 01, C will be 10, and D will be 11. Okay, so you're sending 2 bits for every one of them. That's the minimum you can send. That's what the theoretic lower bound is telling you. Okay, now if the probability changes, okay, if probability of A is equal to 0.5, probability of B is equal to 0.3, and probability of C and D is equal to 0.1, if we compute the entropy given these probabilities, we find like actually we can go lower than 2 bits. We don't need to send 2 bits. Okay, we can actually in average send 1.35. This is the average code length. The minimum average, the theoretic lower bound is 1.35. That may not be practically achieved, but at least it tells you like this is a theoretic lower bound. Then you can design your code, okay, to actually try to reach that lower bound. And one choice here I give, for example, here, you can actually send 1 bit when you are sending 1 because 1 has the highest probability, okay? So you are sending 1 more frequently compared to others, then it's okay if I send only 1 bit for A versus 3 bits for D because I rarely send D. Most of the time I send A. Then I don't need to send 2 bits for each one of them. I can go high for this and low for that. And I'm still saving in terms of the average code length, okay? Because this is, I know I'm sending 3 bits here, more than 2 bits, okay? But actually, I rarely send D, okay? D has very low probability of occurrence. So most of the time, I'm sending A. So then I give 1 bit here, 2 bits for B, 1, 0, 1, 0, 0, 1 for C, and 0, 0, 0 for D. So for this, I give 3 bits, but I rarely send these two compared to these two. Then if I compute the average code length, has a probability of 0.5. This probability of occurrence equal to 0.5 times 1 bit. I send 1 bit for this, plus 0.3 for the other one. That's the probability of occurrence of symbol B, times 2 bits. I'm sending 2 bits for this one, plus this is the last two, C and D. Both of them has probability of 0.1, and I'm sending 3 bits for each one of them. And I was able to, on average, achieve 1.7 bits. So I'm sending, compare this with this. Okay, when they are equally probable, I cannot send more less than 2 bits. But here, when they are not equally probable, I designed this code which can send an average 1.7 bits. It's still higher than the theoretical upper bound. Maybe there could be a better way, like I can still actually go lower in the number of bits, but at least this is lower than like the case when they are equally probable. Okay, so yeah, what will happen if the probability of if A is equal to 1 and all of the others are zeros? Then in fact, I don't need to transmit anything because the receiver knows that I'm like every sample I have is A, and whatever I'm going to send is going to be equal to A. Then the entropy is equal to 0, and I don't really need to send anything. And just I forgot to mention, this is like, I'm assuming like a random variable X that can take one of these choices, okay, or samples, okay. So yeah, when probability of A is equal to 1, then and everyone else is equal to 0, then actually I don't need to transmit. Okay, the entropy is equal to 0, so the average code length is equal to 0. So you don't really need to send any bits. That's where the word bits is coming from. I don't want to go much more into the details. I think I already did went in like in more details than you may need for 291, but yeah. Anyways, so that's like where the unit bits is coming from. Yes. So here, actually what we do, actually we did that, okay? So here we're trying to vary the probability B between 0.1 and 0.9. So we don't consider 0 and 1 because that will create an error. Okay, so we actually, yeah, we create like, so we know this function, right? Line space, okay? So we start with probability 0.1 and we introduce 9 steps until 0.9. So then we will go 0.1, 0.2, 0.3. And for each one of these, we will compute the entropy. Okay, this is list comprehension, right? This is a concise way of creating a loop, right? So we're going to go over every value of P in capital P. So we're going to go from 0.1, 0.2, 0.3. And for every choice of P, we're going to compute the entropy of P. That's like one way to do it. So we hard code the function that computes the entropy. There's also another way here. We can use scipy.stats. We import entropy function from there. Then we just need to call the entropy function. If we call the entropy, then we just need to pass the P and 1 minus P. These are the two probabilities. Okay. And the base is equal to 2. Okay. As I said, we're computing, so we are computing here the number of bits. Okay. So we use log2 for that. Okay. So again, so in old calculators, we use not to have a choice or button to compute log for base 2. So if you don't have that, then you need to compute the log of your variable and divide it by log2. That will give you log for base 2. Okay. So then, yeah, that's it. So this is the function entropy. It takes these two input arguments, the probabilities, and the base for 291, or for the type of entropy we're computing, the base will always be 2. Okay. We are computing it for every P. And this is what we get. As you can see, the entropy starts low. And as we proceed, when they are equally probable, when B equal to 0.5, the value will be 1, and it will start decrease after that. Okay, because now as B decreases, 1 minus B increases, and the uncertainty is going lower. Okay, so and this is here we plot it actually. Okay, so and we have already explained this figure. I don't need to go over it once more. So this is the entropy versus the probability. As we increase the probability, it increases up to B equal to 0.5 and then starts to decrease after that. Maybe let me also explain information gain, and then we stop after that, okay? So this is the formula of the information gain. So the information gain, the gain we gain from knowing B, okay, is equal to entropy of A minus entropy of A given B. So now take our example, okay? Entropy, like the information gain we gain by knowing that the subject, what the value of subject is, okay? The gain of the information we gain for the target variable, the color, will be equal to entropy of color minus entropy of color given the subject. And entropy of color given the subject is equal to 0. Then the information gain will be equal to entropy of color. So the information gain will be at its highest value when the conditional entropy is at its lowest value. Okay, so that tells us like this feature is telling me everything I need about this feature. Okay, now when these two features, when B doesn't tell me anything about A, then the conditional entropy of A given B will be equal to entropy of A, because actually it doesn't tell me anything. It's totally unrelated or independent of A. So then this will be equal to entropy of A. So I will be as uncertain about A as I used before knowing B. So then the entropy of A given B will be equal to entropy of A. And the information gain will be entropy of A minus entropy of A, that's equal to 0. So we don't gain anything, okay? We don't gain any information on A by knowing B, okay? And we're gonna come to more about that later on. Maybe let me run this this video here to see what it tells us, okay? So here, what do we have? Yes, so this is actually, yeah. So this is our example, right? So entropy of the information gain is equal to entropy of color minus entropy of color given the subject. And since entropy of color given the subject is equal to 0, then the information gain is equal to entropy of color, which is equal to 2.32. So we gain so the subject is telling me everything I want to know about the color. Okay. With that, we come to the end of this lecture. We will continue from here next time. Thanks for watching. Salam alaikum.